Okay, now we're getting into Bernoulli equations. And so the first one says that water enters your home plumbing at ground level. Where will you get the strongest spray from a shower? In the ground floor shower, in the basement shower, or on the second floor shower? So clearly what you have is that you've got three floors: the basement, the ground floor, and then the second floor. So let's go ahead and get rid of this. And so the idea about Bernoulli's equations is that essentially what it is that it's conservation of energy. So that as long as things are conserved, you have the pressure potential energy. This is the pressure of the water, plus the kinetic energy of the flow of the water. And it could be any fluid, so we'll just leave it as rho, times the velocity squared. And then you also have the gravitational potential energy. This essentially is the energy per unit volume. And the idea is that as long as you don't have any losses, which essentially is what Bernoulli's equations assumes, then the total energy per volume is a constant. Since you've got a fluid, you've got twice as much fluid, then you get twice as much energy. So it makes sense to normalize the energy by the actual volume. And so the idea is if you have a house which has three floors, you've got essentially the basement, the ground floor, and then basically the second floor. The feeder pipe comes in at the ground level. And so the idea is that if it comes in at some pressure and some flow, the general idea is that if it's down at the bottom, so you've got some feeder pipe and part of it goes down, part of it supplies the second floor bathroom, and part of it supplies the ground floor bathroom, say if you have three different bathrooms, or if you have an apartment building for that matter. The idea is that since, let's just assume that the flow is always the same, if the potential energy decreases, that means the pressure goes up. And so the pressure will be highest basically in the basement. It will be basically in the middle, essentially in the ground floor. And it will be the lowest pressure essentially on the second floor because it's higher up. This essentially is also consistent with the idea that the pressure as it changes, the depth of the water is just equal to P atmosphere plus rho GH. So the farther you are down, the higher the pressure. But Bernoulli's equation is what really does that. So essentially, if everything's constant, then assuming that the flow rate is the same, then as you decrease the potential energy, the pressure potential energy has to increase to compensate. Which means that as far as the pressure which is driving what's coming out of the shower head will be largest in the basement and weakest on the highest floor. And so you'll get the strongest spray basically in the basement shower, which is in 2. And you kind of know this. Now the idea about this, essentially what's frequently used is the idea of the equation of a continuity, which really what that means is that the flow of water as it goes into a pipe has to be equal to the flow coming out of the pipe. And so if the cross-sectional area increases, then the velocity decreases as it flows. The flow rate, which is basically the meters cubed per second, basically, is the volume of water that flows through the pipe at any given instant in time. So again, Bernoulli's equation basically says if there's no energy losses, then you can always look at how the kinetic energy changes and the gravitational potential energy and the pressure. And we'll use a couple different examples of that. So this one's fairly similar, is that a single pipe delivers water to all 4 floors of a house. Let's suppose that you have an apartment building. Ignore any effects due to viscosity, meaning that there are no energy losses. We're going to talk about that at the end on Tuesday. Compared to water flowing to the basement bathroom, water flowing to the attic bathroom has less total energy per liter but the same pressure, the same total energy per liter but less pressure, less total energy per liter and less pressure, and the same total energy per liter and the same pressure. And the idea there is just like what I said before, is that if you have very similar, so you have 4 floors, in terms of height. The idea is that at every point, let's just assume that you have, some pipe that's going in there, and then it rises up to the 4th floor. At every point, Bernoulli's equation says that the energy that you have is a constant. And so everything else being equal, as the gravitational potential energy goes up, the pressure potential energy has to decrease in order to compensate. And so, but at every point, the total energy that's contained in the per unit volume essentially is a constant because it doesn't have any losses. So in this case, it has the same total energy per liter, but it has less pressure as you go up into the upper floors. So if you get to the 4th floor, the attic, then you essentially have less pressure, but the same total energy per liter. This next one's sort of similar. You decide to water a small tree behind your house at the top of a hill. You turn on the outside water spigot so that your 3/4 inch diameter garden hose carries water moving at 10 centimeters per second. As it goes up the hill from your house, it asks what about the pressure and the velocity. So, same deal. Slightly different picture, but one that you probably know. So you have some house at the bottom of the hill. You have a hose that you open up a spigot, and you imagine that you have a hill where you've got some tree at the top of the hill, and the hose runs up the hill. Seemingly, I can't draw it, but the idea is that the diameter of the hose doesn't change. And the idea about continuity is that whatever the velocity is that's coming out of the house, assuming that because water is not compressible, that means the velocity everywhere in that hose essentially is constant because the cross-sectional area of the hose never changes. And so Bernoulli's equation essentially says that since the kinetic energy never changes, the only choice essentially as the gravitational potential energy increases, because the kinetic energy is a constant, is that the pressure has to go down as you go up the hill. And at every point, basically, what you have is that the total energy is a constant because you don't have any energy losses. So in this case, basically, as you go up the hill from the house, the pressure is less, but the velocity stays the same. And so the only one that matches that is basically c. So as the gravitational potential energy increases, the pressure has to decrease, but the velocity always stays the same because essentially water is incompressible. And then we have one last one, which is a 2-inch diameter pipe carries water moving at 10 centimeters a second. The pipe suddenly narrows down to 1/2 of an inch diameter pipe. Which of the following statements is true? So So the idea is that you have essentially some pipe, and you can assume that the cross-sectional area basically decreases. And so what that means is that if it has some flow in some unit time delta t, and you have this cross-sectional area, this is the volume of water that goes in for every, say, time delta t, or every second, if you want to look at it that way. And in order to make it continuous, because the cross-sectional area for the thin section decreases, what that means is in order to get the same sort of volume flow, is that the velocity has to increase. So this basically goes up as the cross-sectional area goes down. And what that means is the kinetic energy increases. And so again, Bernoulli's equation says that rho v squared plus rho gy is equal to a constant. And for this case, we can just assume that essentially this doesn't change. But the kinetic energy clearly increases, and the only choice, basically, is that the pressure has to decrease. This is actually the one which seems to be the most nonsensical. It's really hard to get your head around it. But the idea is, as the velocity increases, because the energy is a constant, the pressure has to decrease as you go into the thin section. And so the water in the half-inch pipe moves at a higher speed, but the pressure is lower than it is in the 2-inch pipe. And so B is the only possible answer.